Welcome to this deep dive, and we are going to be focusing on how to optimize hydraulic fracturing treatments for oil and gas wells.
Cool.
And, we know our listeners are super interested in understanding how engineers go about actually designing these treatments and then how those decisions end up impacting how much oil and gas a well actually produces.
Yeah, that's a great topic, and that's a question we get a lot.
Yeah,
Yeah.
definitely. So to help us tackle this topic, we've got a great technical chapter that's you know, pretty in-depth on the engineering aspects of hydraulic fracturing
Okay.
and how it impacts production. And then we also have a cool visual aid to help illustrate some of the key concepts, and that's an electrical resistivity analog model.
Nice.
Yeah. So, all right, let's jump right in because we know that the ultimate goal here is to maximize what you get out of a well after you fracture, right?
Yeah, definitely. It's all about maximizing that post-fracturing performance, and that's really key for economic success, making sure these wells are actually profitable.
Right. Absolutely. So, okay, let's start with permeability because that seems to be a really crucial factor based on our sources.
Yeah, for sure. Permeability is essentially a measure of how easily oil or gas can flow through the rock formation.
Okay.
And it's kind of like a highway system. You can think of it that way.
Okay.
So like a high permeability reservoir is like a wide open highway, multiple lanes, traffic's flowing smoothly.
Correct.
But then a low permeability reservoir is more like a two-lane road, a little bit narrower, a lot less capacity for flow.
So it's like when you're designing the treatment, it's like you got to figure out what kind of roads you're dealing with first.
Exactly. You got to know your roads before you can plan your route, right?
Yeah.
So understanding the permeability is like figuring out what kind of highway system you're working with, and that helps you choose the right design approach because sometimes you need long stretches of highway.
Right.
And sometimes it's more about having a lot of on and off ramps, to get the traffic flowing.
That makes sense. And, speaking of design, our sources talk a lot about the balance between fracture length and conductivity.
Yeah, those are key factors.
Can you just break those down for us? What are those and why are they important?
Sure. So fracture length is pretty straightforward. It's basically how far those fractures extend into the formation.
Okay.
And conductivity is all about how easily the oil or gas can flow through those fractures.
Wow.
And they're both really crucial because you need to balance the capacity of the fracture to carry the hydrocarbons with the ability of the surrounding formation to actually supply them.
Okay.
And it's kind of like that highway analogy again, You want a highway that can handle tons of traffic,
Right.
but you also need those feeder roads that can efficiently get all that traffic onto the highway in the first place.
Gotcha. So if the fracture is like the highway, then conductivity is like having good feeder roads.
Exactly. And there's this ratio that engineers use called dimensionless fracture conductivity, or CFD.
Yeah.
And that basically helps them strike the right balance between length and conductivity. Our sources say that ideally you want to aim for a CFD of around 2,
Okay.
which is kind of like finding that sweet spot where your highway can handle all the flow of traffic that your feeder roads can supply.
Gotcha. So 2 is the magic number.
Yeah, you could say that.
Okay, cool.
Yeah.
So let's get into some real world examples here because I think that'll help make this a little bit more concrete.
Sounds good.
So, one of our sources talks about the Muddy J sandstone in Colorado, which is a tight gas formation. So I'm thinking back to our 2-lane road analogy.
Right?
So tell me, how does fracture design play out in a situation like that?
Yeah, so in these tight formations where the permeability is low, remember those 2-lane roads,
Yeah.
longer fractures actually tend to be better.
Interesting. Why is that?
Well, because the formation itself has a hard time supplying gas efficiently.
Yeah.
Those narrow roads, it's tough to get the traffic moving.
Right.
So what you're doing with longer fractures is you're basically creating a shortcut so that the gas doesn't have to travel as far on those narrow roads.
So you're short-circuiting the system.
Exactly. You're giving it a faster route.
I like that.
But then in a moderate permeability reservoir, more like our multi-lane highway analogy,
Right.
increasing the fracture length beyond a certain point, it doesn't actually give you that much extra production.
Interesting.
Yeah, because the formation can already supply the gas pretty effectively. So those extra long fractures, they're kind of overkill at that point.
It's like adding extra lanes to a highway that's already flowing freely.
Yeah, exactly. It's not going to make that much of a difference.
So it really is all about understanding that permeability from the get-go
Yeah, you got to know your reservoir.
to figure out which strategy to use.
Absolute.
Okay, cool. So now I want to ask about something called equivalent wellbore radius, because that's a term that I saw come up in our sources, and it sounds kind of complicated.
Yeah, it sounds fancy, but it's actually a pretty simple concept.
Okay.
Basically, it means that the fracture acts like an extension of the wellbore. So it increases the area where the oil or gas can flow into the well.
Gotcha.
So instead of just having that small well bore, you've got this much larger surface area thanks to the fracture.
And that bigger surface area helps you get more production, I'm
Anyway,
guessing.
you bet it's like opening up more doors for the oil and gas to come in.
Yeah.
And that's where the term folds of increase, or FOI, comes in.
All right.
FOI is basically a way to quantify how much production has improved after you've done the fracturing treatment.
Okay.
So it helps engineers compare different treatment designs and see which one gives them the best bang for their buck.
That makes sense.
And you know what's interesting is that even a less than ideal fracture design can still give you a good FOI.
Really?
Yeah, as long as it increases that well bore radius enough.
Interesting.
One of our sources had an example where a treatment with a CFD of less than 1, remember we said we want to aim for 2,
Right.
but it still resulted in a significant production increase because even though it wasn't the most efficient design, it still effectively increased that well bore area.
So it's like, even if you take a bumpy detour, you can still get to your destination faster than if you just stayed on the main road.
Exactly. Sometimes a detour is the way to go.
Okay, so now let's talk about drainage boundaries, because I know those can play a big role in fracture design as well.
Yeah, for sure.
Can you explain, like, what are those and how do they impact things?
So drainage boundaries are basically anything that limits the extent of a fracture.
Okay.
Think of it like city planning. You know, if you have a city with limited roads,
Okay.
building a huge highway might not actually be that helpful
Interesting.
because the existing streets can't feed enough traffic onto it. You know, it creates bottlenecks.
Right.
And in the same way, things like faults or the spacing of wells, these can create boundaries that limit how effective a fracture can be.
So even if you have a great fracture design, those boundaries can still create bottlenecks.
Yeah, exactly. They can kind of put a cap on how much production you can get.
Gotcha.
And we actually have that visual aid that I mentioned earlier, the electrical resistivity analog model.
Right.
That was developed by McGuire and Sikora, and it shows really nicely how drainage boundaries can affect fracture effectiveness.
Okay.
So treatments with a low CFD, you know, kind of like our city with limited roads,
Right.
they're actually less affected by boundaries.
Interesting.
But then treatments with a high CFD, you know, the ones you typically see in tight formations,
Okay.
those can actually benefit from longer fractures, even when they're close to boundaries.
So it's like in that situation, the longer fracture is helping overcome those bottlenecks.
Exactly. It's like building more on-ramps
Yep.
to help get that traffic flowing.
Okay, cool. So now I want to switch gears a little bit and talk about acid fracturing,
Sure.
because I know that's another technique that's used to enhance production.
Yeah, it's a different approach.
So how does that compare to propped fracturing, and like when would you choose one over the other?
Good question. So they both aim to create conductivity, but they work in different ways.
Okay.
Acid fracturing is kind of like etching flow paths with acid. You know, you're dissolving the rock to create those channels. While propped fracturing uses those tiny particles called proppant to physically prop open the fractures.
There's like acid is dissolving and proppant is like physically holding them open.
Exactly.
Okay. And how do they compare in terms of like effectiveness?
Well, acid etching can potentially create really high conductivity, but it's limited in terms of length.
Okay.
Whereas with prop fracturing, you have a lot more control over the length, but you might not get quite as high conductivity.
So it's a trade-off.
It is, and that's where those FOI calculations come in handy.
Right.
They can help you evaluate that trade-off and figure out which technique is going to give you the best results.
Okay.
But of course, there are other factors to consider too, like, you know, the compatibility of the formation with the acid or the proppant, and also things like wellbore considerations.
Right. So there's no one-size-fits-all solution.
No, it's all about tailoring the approach to the specific well.
Okay.
Right.
Okay, so one last thing I want to ask about before we wrap up this part of our deep dive is this concept of transient flow.
Oh yeah, transient. Love it.
Can you explain that to me? Because it sounds kind of mysterious.
It is kind of cool. It's basically a temporary boost in production that you get early on after you've done the fracturing.
Okay.
And it happens because the pressure dynamics in the reservoir are still kind of adjusting, you know, everything's settling down.
Right.
And we see these different flow regimes or phases.
Okay.
And transient flow is typically associated with the first 3 of those regimes.
Okay, so you have these different flow regimes, and I'm guessing understanding those helps you kind of predict how much oil and gas you're going to get and when.
Exactly. It helps you forecast production.
And I imagine that's really important for planning purposes and for, you know, making sure these wells are actually economically viable.
Absolutely. You got to know what to expect.
Right.
And one of our sources actually had a really interesting case study where a well had a 55% increase in cumulative gas production over 3 years because of transient flow.
Wow, 55%. That's a huge impact.
It is, and it just shows how important it is to understand transient flow and how to actually maximize its impact, because it can make a big difference in terms of optimizing production and making sure those wells are profitable.
Yeah, absolutely. This is all incredibly insightful. We've covered so much ground. We talked about permeability, we talked about balancing fracture length and conductivity equivalent, wellbore radius drainage boundaries, and now this fascinating phenomenon of transient flow.
Yeah, it's a lot to take in, but hopefully you're starting to see how all these pieces fit together to optimize those fracturing treatments.
Yeah, absolutely. And I think, now that we've laid the groundwork, we can really dive into like the nuts and bolts of how engineers actually go out designing these treatments.
Yeah, let's get into the details.
So stay tuned for part 2, where we'll do just that.
So are you ready to get into like the actual nuts and bolts of designing these treatments?
Yeah, let's do it.
Yeah.
What are some of the things that engineers are thinking about when they're actually designing these hydraulic fracturing treatments?
Oh, one of the first things they got to consider is the proppant.
Right, the proppant. So that's those tiny particles that we were talking about that hold the fractures open like the feeder roads.
Exactly. And you actually have to choose what type of proppant you're going to use because it directly impacts how well those fractures stay open and how easily that oil and gas can flow.
So what are like the key things that you think about when you're choosing a proppant?
Well, strength is a big one.
Okay.
You got to remember all that weight from the rock that's sitting above.
Right.
So the proppant needs to be strong enough to actually hold up under all that pressure and keep those fractures from closing.
So are there times when you would want to use a weaker proppant, like if it's a shallower well or maybe the cost savings are worth it?
That's a really good question. And yeah, cost is definitely another factor.
Okay.
Stronger proppants, they tend to be more expensive.
Right.
So engineers have to kind of balance, performance and budget.
Right.
Sometimes a weaker proppant is totally fine, especially if the pressure in that reservoir isn't too intense.
Yeah, that makes sense. It's like choosing building materials. Sometimes you need the reinforced steel and sometimes good old lumber will do the trick.
Okay, cool.
And then another thing to think about is the size of the proppant particles.
Okay, how does that play in?
Well, larger particles create wider channels for the fluid to flow through,
Okay,
which means you get better conductivity.
so bigger is better.
Well, not always.
Right.
Sometimes those larger proppant particles can actually be harder to get downhole.
Okay.
It's kind of like trying to fit a big truck through a small tunnel,
Okay. Yeah.
Sometimes those bigger particles can get stuck and clog things up.
So it's always a balancing act
Yeah, for sure.
between strength and size and cost.
Yep.
Okay, so what else are engineers thinking about when they're designing these treatments?
Well, the fracturing fluid itself is really important.
Okay.
That's the fluid that's actually carrying the proppant downhole, and it's helping create those fractures in the first place.
So what are like the different options for fracturing fluids? Oh, there are a bunch, ranging from simple water-based fluids to thicker gels and even foams.
Wow. So how do you choose the right one?
It depends on the formation that you're working with.
Okay.
So for example, if you need to create long fractures, you might need a thicker fluid, like a gel, to keep those fractures from closing too quickly.
Okay, so thicker fluid, longer fractures.
Yeah, and then if you're working in a more challenging formation, like one that's prone to fluid loss,
Okay.
you might use something like a foam because it's lighter and less viscous.
So it's all about kind of matching the fluid to the specific challenges of that formation.
Exactly.
Okay, cool. So I'm curious about how do engineers actually keep track of what's happening downhole during this whole fracturing process?
Yeah, it's not like they can just look down there and see what's going on, right?
Right, exactly.
That's where real-time monitoring comes in.
Okay, so tell me about that. What is real-time monitoring?
It's basically like having a window into the wellbore.
Oh.
Engineers use all sorts of sensors and technologies to track key parameters during the treatment.
Okay, like what kind of things are they tracking?
Well, things like pressure and flow rate.
Okay.
And even these tiny tremors called microseismic activity.
Microseismic activity, what is that?
It's basically tiny little earthquakes
Wow.
that happen as the rock is fracturing.
So they can actually like hear the rocks breaking?
Pretty much. And by monitoring those tremors, they can get a real-time picture of how those fractures are growing and spreading.
That's amazing. So it's not just a set it and forget it operation anymore. They're actively like controlling the process as it's happening.
Exactly. It's very dynamic.
Wow, that's so high tech.
It is real-time monitoring has really changed the game when it comes to hydraulic fracturing.
How so?
Well, it makes the process more efficient, it helps minimize risks, and it ultimately helps maximize production.
Those are all good things.
Yeah, for sure.
I bet this technology doesn't come cheap, though.
You're right, it is an investment.
Okay.
But it's one that often pays off in the long run, especially when you consider the potential cost savings and the increased production.
So it's like you're paying for a really good GPS system. It might cost a bit more upfront, but it helps you avoid wrong turns and get to your destination faster and more efficiently.
I like that analogy.
Cool. Well, we've covered a lot of ground here. We talked about proppant, the fracturing fluid, the importance of real-time monitoring,
It's a lot to take in.
but I know there's even more to the story, right?
Oh, yeah, we haven't even touched on some of the really cutting-edge technologies that are being used to optimize these treatments.
Okay, like what?
Things like fiber optic sensing and even artificial intelligence.
Wow, that sounds fascinating. I'm definitely ready to hear more about those. Okay, so let's talk about those cutting-edge technologies. What is this fiber optic sensing all about?
Okay, so imagine these like incredibly thin, hair-like fiber optic cables, and they're running alongside the wellbore deep underground.
Okay, I'm trying to picture it.
Yeah, so these cables, they act as super sensitive sensors,
Okay.
picking up even the tiniest changes in temperature strain, acoustic vibrations.
Wow, so it's like they're giving you a real-time checkup on the well, like listening to its heartbeat.
That's a great way to put it. Yeah, fiber optic sensing gives us this constant stream of data so we can really see what's happening down there in incredible detail.
So like what kind of things are you actually seeing with this technology?
Well, one of the most valuable things is that we can actually map those fractures in amazing detail.
Really?
Yeah, we can see how they're growing, how they're branching out, even how they're interacting with each other.
So it's like having X-ray vision for your well.
Pretty much.
Why is it so important to be able to see the fractures like that?
Well, it helps us optimize the entire treatment.
Mhm.
If we know exactly how those fractures are forming, we can make better decisions about proppant placement, fluid volumes, even well spacing.
So you're making sure that those fractures are really doing their job, creating those pathways for the oil and gas to flow.
Exactly. We want those highways open and flowing.
Right. And you said that fiber optic sensing can also help monitor proppant settling. What is proppant settling?
So sometimes the proppant doesn't stay perfectly suspended in that fracturing fluid.
Yeah.
It can start to settle to the bottom of the fracture.
I'm guessing that's not good.
Not really. No, when the proppant settles, it can block those nice wide channels that we've created and make the fracture less effective.
So how does fiber optic sensing help with that?
Well, remember how I said those cables can detect tiny changes?
Yeah.
They can actually pick up the settling of the proppant, so they can tell us if it's distributed evenly or if it's starting to clump up in certain areas.
That's wild. It's like those tiny cables are reporting back from the front lines,
Exactly, giving us those real-time updates.
letting you know what's going on down there.
Yep, and then we can use that information to adjust the treatment as needed, make sure the proppant is right where it needs to be.
To me, it really sounds like fiber optic sensing is changing the game when it comes to hydraulic fracturing.
It really is. It's a game changer.
So what other technological advances are we seeing on the horizon?
Well, one area that's getting a lot of attention is artificial intelligence.
AI for oil and gas. How does that even work?
So these AI algorithms can analyze huge amounts of data from all sorts of sources, real-time monitoring, geological surveys, historical well performance.
So they're like super-powered analysts crunching all those numbers and looking for patterns.
Exactly. And AI can identify trends and correlations that humans might miss.
So what kind of insights can AI provide that actually help with these treatments?
Well, it can help optimize things like fracture design, proppant selection, even predict how much oil or gas a well will produce.
Wow,
It can even help anticipate potential problems before they happen.
that's incredible. It's like having a virtual expert guiding every step of the process.
Yeah, it's pretty powerful stuff.
Mhm.
And AI is still in its early stages, for the oil and gas industry,
Yeah?
but it has huge potential to really revolutionize how we approach hydraulic fracturing.
Wow, this has been an incredible deep dive. We've gone from like the very basics of permeability to these mind-blowing technologies like fiber optics and AI.
Yeah, it's been quite a journey.
It really has, and I think it highlights just how much science and engineering goes into optimizing these treatments and ultimately maximizing oil and gas production.
Absolutely. It's a complex process.
It is, and it's clear that understanding the reservoir, designing the right treatment, and then using the right technologies all play a crucial role.
It's all about working smarter, not harder.
Exactly, and doing it responsibly too.
Of course, we want to be good stewards of our resources.
Absolutely. Well, I have to say, you've given me a whole new appreciation for what goes on behind the scenes in the energy world. This has been fascinating.
I'm glad you enjoyed it.
I did. And to our listeners out there, thanks for joining us on this deep dive. We hope you learned something new, and we'll catch you next time for another deep dive into the world around us.